You remember in the previous two learning sequences, we discussed a lot how to actually estimate effects, how to test if the effects are significant, also how to visualize the effects. For example, we used the main effects plot, interactions effects plots, we used Toki plots for the difference of means and so on. However, sometimes, especially in commercial software, you will see another way of representing your effects, and it's called Pareto chart for standardized effects. For example, this is what you can see in if you use Minitab software, one of the very famous software for statistical analysis. And then you can see that in this case, we also have a design. It's actually full factorial design with 3 levels. So you can see that these are the main effects. These are interaction effects with 2-factor interactions. This is 3-factor interactions effect, right? Then what you see here is that every effect is represented as a bar with what is called a standardized effect. So these are some numbers, some standardized numbers. And then you can also see that this is, for example, the level for kind of a critical level. So it means that if effect is smaller than this one, then this effect is not significant. So in this case, I believe they work, yes, indeed, with 95% confidence, right? Let me explain the meaning of this plot and also how to make this plot in R. Okay. Let's get back to our first example. One of the first example, it's pilot plant investigation. You remember it's the investigation when we use 3 factors and we investigate how these factors influence the yield of a certain chemical reaction. The factors are temperature, the concentration of catalyst, and the catalyst type. And then we use double runs, so it means that we have 16 runs in total. And then remember, we calculated variance. How? Because we have 2 runs, we can calculate variance of every trial, right? So for example, variance of this trial is 2, and then you use 1 degree of freedom here. Then it's 8 with 1 degree of freedom, 32 with 1 degree of freedom, and so on and so forth. And then you can compute a sum and average pullet variance. In this case, pullet variance is 8, and then it means that because you take a sum of 8 kind of independent variance values, you have the degrees of freedom is also 8 here. Right? What else you can do? What's next you can do? You can compute what is called a standard error. A standard error is, we use a t-test to compute standard error. You remember that this is a variance for the first, for example, 4 trials, right? And then this is the a variance for the second 4 trials. For example, this is the variance when temperature was 160. This is the variance when temperature was 180. And then because we use a pullet variance, it's the same in both cases. So this is the way we computed standard error here, right? Now, what you can do the following. First of all, I used a little bit more decimals here just to make the calculations precisely. This is the table you remember that we made before, right? This 3, it's approximately 2 point something standard errors, right? So this is our error margin. It doesn't actually important now, so I will just get rid of it. So these are our effects. So this is the observed effect. This is the effect that we observe. And now look, this standard error, it gives you a level of noise, right? What you can do, you can take an effect to noise or signal to noise ratio. So you take an effect and divide to noise. Or it will be a difference, right? So you remember it's a difference, for example, when temperature is 180 minus difference when temperature is 160 divided to standard error, right? But what is it? Because we are talking about average values and standard errors and so on and so forth. So remember, we use t-distribution. So this is nothing else, but it's a standardized value from the t-distribution. It's a t-score. And that's exactly what we call a standardized effect. So it's a t-score. It tells you how bigger the observed effect is compared to standard error. So how many standard errors you have in the observed effect. Okay. So let me do the calculations. For example, if you take 23 and divide to 1.414, you will get 16.3. The meaning of this value is following. The observed effect, it's 16 times larger than the standard error. Here you have -5. And you can see that I got rid of the sign. I need only the magnitude in this case. So 3.5, what it means again? It means that this observed effect, it's 3.5 times larger than standard error. So now we have the same effects, but not in, for example, in milligrams or whatever units we use for the y values, but we have them in standard errors. So this is effect measured in standard errors. standard errors, which is a level of noise, right? And then what else we can do? We can also like sort this effect. So we have this is the biggest, this is the next biggest, this is the next biggest, and so on and so forth. And that's exactly the height of the bar, so the length of the bar. So this is the size of the first bar, second bar, third bar, and so on and so forth. So we can visualize it like this. You can see? So this is standardized effect. You remember that this one is 16.3, so this is exactly 16.3. Okay. And then you remember that we also can do the same things in ANOVA. You remember that ANOVA, it's like a generalization of t-test, right? So you remember, at least I showed you how to calculate standard error based on the residual variance like this, right? However, in this case, you can also get all the standardized effects from the f values, because remember what is f value? F value, it's the ratio of two variances, the systematic variance, and the noise variance, the random variance, right? You remember in t-square we have effect to noise, to standard error, right? But it's just a t value squared, so the f value from ANOVA is just a t squared value, at least in case where we have only two levels for the effect. And you can check it quickly. For example, if you take this as the f value, 264 for the temperature, 0.5. If you take a square root of 64.5, you will get approximately 16.3. This is exactly the value you have here. If you take a square root of this, square root of 12.5, you can check it, please check it now. And then you will see that this is 3.5, this is exactly the effect that we have here, and so on and so forth. So it means that we can actually make a Pareto chart based on the ANOVA model. So we can provide this M, extract of all f values, take a square root of all f values, and then we can actually make a chart. Moreover, we can also compute a critical value, right? So remember that we have, for example, for temperature, the f critical will be you remember that we have a distribution, f distribution. This is the f value we observe, and this is the p value, right? And then you can, for example, make a critical, you can find a critical f value. So here you have 5%. So it means that it's for 95% cases, right, when null hypothesis is true. So you can compute this f critical value by using, for example, QF. It's a quantile function for f distribution, 0.95, and then 1 degree of freedom for a systematic variation. This is 1, right? And then 8 degrees of freedom for the random variation. Okay, and then you can compare these values with the critical value and then make a decision based on that. That's exactly how this is done. But here we compare the p values with 0.05 instead. Okay, so this is it. So I computed this critical value and I got 2.31. This is this level. So any effect which is larger than this 2.31 will be considered as significant. Okay. And then if, for example, you cannot compute the critical value, if you cannot compute the noise level, you can make this plot without this level of the critical value level. Okay. So that's the Pareto chart for standardized effects, and that concludes this short learning sequence about something extra in variable screening. And we have only a couple of videos left where we are going to talk about how to do things in R. First of all, I'll show you how to make the Pareto chart in R based on the ANOVA model. That's what the first video will be about. And then the second video for the R, we will do something which is called code cleaning. So we will clean our code and write some comments and help text. Okay, let's proceed to the next video.